This study targets domestic service robots that can understand natural language instructions for manipulation tasks. We aim to understand fetching instructions from linguistic and visual modalities in an end-to-end approach. A typical fetching instruction is: take the teddy bear sitting in profile on the right-hand table. To solve this multimodal language understanding task, we consider as input an instruction as a natural sentence and an image of the environment. The output is then the most likely target and source. In this study, we consider a home environment context. Typically, a domestic service robot is patrolling in an indoor scene and collect images containing daily life objects and pieces of furniture. These objects and pieces of furniture are the candidate targets and candidate source. To solve this task, we propose the multimodal target source classifier with attention branches, MTCM-AB. This network is composed of 3 attention branches. What are attention branches? Initially, attention branch network intends to improve classifiers by separating a network into branches: an attention branch and a main network branch. While these branches predict the same labels, the attention branch outputs an attention mask that highlights the most salient part of the feature related to a given label. This attention mask is used thereafter to improve the main network accuracy. Let us detail the MTCM-AB network structure. The visual inputs are the candidate target, heuristic features that characterize the position of the target in the image, a neighboring context that is an extended cropped image of the target, including its immediate surrounding. The linguistic input is simply the instruction as a natural sentence. The outputs of the MTCM-AB are the likelihood of the candidate target and source. Target cropped image is processed by a CNN followed by the target attention branch. This branch is composed of fully connected layers and maximizes the cosine similarity through a hinge loss function between the target features and the instruction. The attention branch emphasizes the salient part of the target features that are related to the initial instruction. The context features are extracted from the image and processed in the neighboring context attention branch. This branch is composed of convolutional layers. Similarly to the target attention branch, a hinge loss function is minimized. Lastly, in the linguistic attention branch, the sentence is tokenized into subwords and embedded by using BERT. The subword vectors are processed by a bi-LSTM followed by one-dimensional convolutional layers. This branch emphasizes the linguistic features that are related to the target. The enhanced linguistic and visual features are then encoded by multi-layer perceptrons. From these multi-layer perceptrons, the likelihood of the target and the likelihood of the source are predicted. The source likelihood is predicted by minimizing a cross-entropy loss function. The target likelihood is predicted by minimizing a triplet hinge loss function. To evaluate the MTCM-AB, we use first a standard dataset about pick-and-place tasks. In this dataset, daily life objects are placed into boxes, and each of them is annotated with an instruction. The MTCM-AB predicts the most likely object given the selected instruction. On this dataset, the MTCM-AB outperformed the state-of-the-art baselines with an accuracy of 90.1%. Further ablation studies showed the benefits of using attention branches. Additionally, there was no statistically significant difference between the MTCM-AB and human-level prediction. The MTCM-AB structure allows visual explanation. The attention map produced by the attention branches overlaid on the input context image highlights the area on which the network focuses given the initial instruction. A second set of experiments was conducted considering synthetic data from a photorealistic simulator. The images were collected from an emulated domestic service robot in a home environment. The accuracy results were also consistent with the first experiment. The MTCM-AB outperformed the baseline methods. Additionally, consistent attention maps validate the relevance of using an attention branch structure to understand fetching instruction. The MTCM-AB could also be validated on a fetching task scenario. Given the instruction, the correct target could be predicted and retrieved by the robot. In this study, we proposed the MTCM-AB, which predicts the likelihood of targets to fetch given an instruction and a visual input. The main novelty is the use of attention branches. The MTCM-AB was close to human-level performance on a standard dataset. The MTCM-AB could also be qualitatively validated by the attended target in the image given the instruction.